Yes, I can do that as soon as I remember to unmute myself. So I'm very happy today to introduce my colleague, Dr. Mary Barsony. I met her because we are both professional astronomers and we've gone to several American Astronomical Society meetings at the same time and hung out. But also, she runs a thing called Tech Trek for eighth grade girls that happens on my campus, sponsored by the American Association of University Women. And the girls spend a whole week learning all sorts of tech things. They go to the observatory on our campus, and we've taught them how to solder and done all sorts of fun activities with them. So, but in her spare time, she still does serious research, and she has an association with the SETI Institute. So I'll let her tell you more about herself. But we had requests for talk with some of the new data from JWST, and I think her result that she's going to show you that came from JWST together with the best radio telescope in the world now that's called ALMA. I think it's a really cool result. So I hope you all enjoy it. And I will turn it over to Dr. Barsony.
You're muted, Mary. Sorry.
We practiced this screen sharing stuff before.
How did that happen? How did I get muted? I don't know.
Oh, I think she mutes everybody at the beginning.
Oh, okay.
Mary did it to you.
Let's see.
Okay, so
you can see my desktop.
Right, just need to go into slideshow mode.
Okay. So, alrighty. So
yes, looks good.
Good afternoon, everyone. It's really a joy to speak to you and to share some recent results from both JWST and ALMA. So it turns out that there's a wonderful synergy between the two telescopes, the James Webb Space Telescope and ALMA, which is the Atacama Large Millimeter Submillimeter Array. And hence, there's the title of my talk, that two eyes, meaning JWST and ALMA, are better than either one alone. They both look at star formation, and what we learned by combining the two is greater than observing star formation with either instrument on its own. So I'll just give you a talk outline. It's organized as follows. After a brief introduction to the observational background, we'll learn about our currently accepted outline of the star formation process based on observations acquired over the last 4 decades. These observations were enabled by the advent of infrared and millimeter astronomy over the same time period. Next, we'll learn why JWST and ALMA are playing pivotal roles for making progress in the detailed study of star and planetary system formation. Finally, we'll present recent results for 2 systems in the same nearby star-forming cloud: a protostellar system less than a few 100,000 years old, and an older, more evolved, but still very young by astronomical standards, 2.5 million year old multiple system. Both examples will highlight how complementary JCMT and ALMA are. So first, the purpose of this slide is to give you a taste for what JWST and ALMA can see in relation to all forms of radiation that make up the entire electromagnetic spectrum. It wasn't until the middle of the 19th century that it was understood that the light our eyes are sensitive to is just one form of electromagnetic radiation. The fact that heat, light, and radio waves are different wavelengths or energies of time-varying, oscillating electric and magnetic fields traveling at the speed of light was first experimentally verified as recently as 1888. All of astronomy was done at visible wavelengths until the advent of radio astronomy in 1930, followed by near-infrared millimeter wave, X-ray, and gamma-ray astronomy starting in the 1960s. The insets at the top of the giant elliptical galaxy known as Centaurus A show the difference between its appearance at visible wavelengths at left and in the combined light of X-ray, visible, and submillimeter wavelengths at right. At the bottom are images of 3 space telescopes and of ALMA arranged in increasing wavelength order from shortest to longest, delineating the spectral regions each can see, starting with Hubble, which has been sensitive from the ultraviolet to the near infrared, the James Webb Space Telescope, which sees from near through mid-infrared, its forerunner, Spitzer Space Telescope, sensitive at near, mid, and far infrared wavelengths, and finally ALMA, ranging from sub-millimeter through the millimeter. So why study star formation at infrared and sub-millimeter wavelengths? This slide summarizes in tabular form the many reasons why both infrared and sub-millimeter millimeter observations are required to probe star formation. First, we need to be able to see past the intervening interstellar dust, which obscures the sites of present-day star formation. The longer the wavelength, the deeper we can see into a star-forming cloud. Next, it turns out that the youngest stellar objects, which are not yet fusing hydrogen to helium, radiate most of their energy at infrared and even far infrared wavelengths, unlike the sun, whose peak energy output is at visible wavelengths. Furthermore, diagnostic spectral lines radiated by hot molecular and atomic gas have their transitions in the near and mid-infrared, and warm dust in the innermost region of planet-forming accretion disks also radiates most brightly in the near and mid-infrared. Interstellar dust particles contain carbonaceous compounds, silicates, and may be coated in various ices depending on their location in a protostellar envelope or accretion disk. Their characteristic oscillations occur at near and mid-infrared wavelengths. A plethora of molecular species diagnostic spectral lines radiated by cold gas in protostellar envelopes and from the outer regions and atmospheres of accretion disks are in the submillimeter and millimeter wavelength ranges. And the cold dust present in both protostellar infall envelopes and throughout accretion disks radiate in the submillimeter and millimeter region. So this slide shows you why we need to go to outer space for mid-infrared and far-infrared observations, and why we need to place ALMA at a very high dry site. Just like interstellar dust blocks our view into the sites of star formation at optical wavelengths, the absorption by the molecules in Earth's atmosphere blocks our view of the mid-infrared, far-infrared, and sub-millimeter sky. As you can see from this diagram, the shaded gray areas, so on the vertical axis, you have the percent of atmospheric absorption, so totally transparent, percent atmospheric transmission. So totally transparent would be the visible, which is nearly 100% gray, or there's part of the radio wavelengths, which is almost 100% gray. But everywhere there's black, that's atmospheric absorption. And so I have indicated where JWST wavelengths are and where a previous infrared satellite, IRAS, was sensitive. And you see that you have to be above Earth's atmosphere in space to explore those wavelengths where the black goes all the way down to 0. And then you also see ALMA over in the sub-millimeter, millimeter. A lot of that is almost completely black. And those absorptions are from molecules in our atmosphere like water, carbon dioxide, and oxygen. So here's an optical image of our Milky Way galaxy where I've marked, oh my goodness. That's terrible. I've marked some of the regions of star formation. throughout our galaxy. And then the dark patches you see are the dust that's composed of minuscule interstellar dust particles, which are commingled with extremely low temperature molecular hydrogen gas, 10 to 20 kelvins, which is about minus 440 to minus 420 Fahrenheit. This is the material that makes up what are called giant molecular clouds, which encompass hundreds of thousands to millions of solar masses of gas and are distributed along the spiral arms of the Milky Way. It is within such structures that young stars are born. And as I've mentioned, the locations of a few well-studied star-forming regions are indicated on this image, like the high-mass star-forming regions, Orion A and B, W44, W51. I'd move my cursor around, but it's black, so it's of no help. So you just have to locate where those places are. And these are the high-mass star-forming regions, by which we mean stars exceeding about 8 solar masses, which are quite rare. The most common type of stars are red dwarf stars, and they have masses of just a few tenths of a solar mass. High mass stars form in large groupings in giant molecular clouds, along with many low mass stars, whereas low mass stars can also form in much smaller molecular clouds consisting of just a few thousand solar masses of gas. And examples of such low mass star forming regions are the nearby Taurus and Perseus molecular clouds. The Taurus-Perseus orbit complex is off to the left corner of the screen there. And the Ophiuchus and Lupus clouds, I've put a cyan square around their location because that's where we're going to explore star formation next. So even as recently as the 1940s, the idea that stars could currently be forming was not yet generally accepted. This all changed with the discovery of deeply embedded infrared bright sources in dark molecular cloud cores. So at left, you see a visible light color image of the Ophiuchus dark clouds. Those are the same ones I had and outlined in the cyan rectangle in the previous slide. So at left, you see a visible light color image of the Ophiuchus dark clouds. Due to their proximity at a distance of just 410 light years, they've been extensively studied. Equivalent objects located at greater distances would be much fainter and viewed in much less detail. The white rectangle on the optical image is centered on what is known as the Rho-Oph cloud core. This area is expanded at right. The background grayscale image is a negative from a red filter image taken from the Palomar Observatory's second sky survey, and the black contours represent millimeter wave emission of the C18O molecule, which is a tracer of molecular hydrogen, which makes up the mass of the cloud core. The visual extinction in this region is extreme, 40 to 100 magnitudes. It's about the blackest part of the sky as far as molecular clouds go. The black square inset on top of the contours demarcates the area covered by the first systematic near-infrared survey of the Rho-Oph cloud core, which took place in 1983. I have the reference down at the bottom. The 20 infrared bright objects discovered in this survey are young stars whose locations are indicated by the black crosses. And these objects are called, among many other names, WL1 through 20 for their discoverers, Wilking and Latta. So here is a schematic cartoon of our current picture of star and planetary system formation. In this slide, we outline our current picture of star and planetary system formation and how it was arrived at. Since young stellar objects radiate most brightly at infrared submillimeter and millimeter wavelengths, The crucial observations necessary to arrive at this picture were made possible by the launch of the first infrared astronomical satellite, IRAS, in 1983, and the sub-millimeter telescopes that came online, such as the James Clerk Maxwell sub-millimeter telescope atop Mauna Kea in Hawaii. And you see on the left a picture of yours truly in front of the JCMT, and the other one's the Caltech sub-millimeter observatory in the background. Both of these facilities are the IRAS and the JCMT are shown in the left panel. So IRAS was launched in 1983 and mapped the entire sky at 4 mid and far infrared wavelengths, 12, 25, 60, and 100 microns, whereas the JCMT came online in 1987. And that's where we discovered the first protostar, which we'll talk about later in this presentation. So combining IRAS observations of embedded sources in row of cloud core with the ground-based near-infrared data I showed you provided complete measurements of the total energy emitted by each young stellar object and its environment across many wavelengths, the so-called spectral energy distribution, and the result samples emission from different physical structures. Near infrared is sensitive to the hot dust in disks, as well as to their scattered light. Mid-infrared samples warm dust in disks, and sub-millimeter detects cold dust structures, including protostellar infall envelopes. Assuming different input physical configurations, such as a central star, a disk, and infall envelope, or just a central star and a disk, and varying the inclination angles of the system, computer models of the expected spectral energy distributions were calculated, and comparison of the computed results with the observations led to the classification scheme for young stellar objects that's still used today and shown in the cartoon schematics on this slide. So pictured here is an artist's conception of the currently understood phases of the formation of a low-mass stellar system and its attendant planetary system. We start from a dense molecular cloud core in the upper left, containing a few solar masses of gas, which is itself embedded in a much larger interstellar cloud. If the conditions are just right, like a shock wave passes through and compresses the gas, the core becomes unstable against gravitational collapse and forms an actively accreting protostar. A protostellar system consists of an embryonic protostellar core, which is growing in mass via the accretion of material from a surrounding accretion disk, which is itself created and maintained by the infall of material from the surrounding protostellar envelope. The accretion process generates powerful bipolar jets and winds, which carry away the excess angular momentum and gravitational potential energy, allowing the collapse to proceed. The discovery of the very youngest protostars, aged tens of thousands of years, required sub-millimeter observations in which your speaker took part using the James Clerk Maxwell telescope atop Mauna Kea, since these objects are so embedded that shorter wavelength light cannot get through. The bipolar jets and disk winds eventually disrupt the protostellar envelope and die down as the supply of infalling material dissipates. The accretion disk is cleared of gas and is the site of planetary system formation. Throughout this process, the central object is gravitationally contracting, being held up against gravity by thermal pressure. Eventually, the central pressure density and temperature of the young star reach conditions amenable to the fusion of hydrogen to helium, at which point we can say a star is born. So further progress in understanding the complex and detailed physics and chemistry involved in star and planetary system formation requires advanced instrumentation. This is where JWST and ALMA come in. So before a more detailed description of the capabilities of JWST and ALMA, I'd like to point out what a teensy patches of sky can be observed with these instruments by comparing their fields of view with that of an Orion Starblast 6 amateur telescope. So last summer, this is the telescope I borrowed through San Francisco Amateur Astronomers Telescope Loaner Program for our Tech Trek Star Party for 90 middle school girls at Sonoma State University. The Orion telescope's field of view approaches 2,500 arcseconds with its 25 millimeter eyepiece, whereas the JWST's mid-infrared imager, observing in its medium resolution spectrograph mode, has a very small field of view, just 3 by 4 arcseconds at the shortest wavelengths, up to 7 by 8 arcsecond field of view using its longest wavelength detector. The ALMA results I'll be showing had fields of view of approximately 22 arcseconds. To drive home just how small JWST's and ALMA's fields of view are, compare the sizes of the red squares. Whereas you could easily fit the entire full moon into the Orion Starblast's field of view, the 20 by 20 arcsecond ALMA field of view would correspond to the approximate size of that Aristarchus crater. And the JWST's MRS instrument, from which I'll show results, would fit in just a small portion of the crater in its field of view. So we're looking at very small pieces of sky with these instruments. So that means that a lot of preliminary groundwork observations must be made first at many other facilities before any follow-up JWST and ALMA observations are obtained. So this is a slide from John Mather, who's one of the senior project scientist of James Webb Space Telescope, just to point out that JWST has 4 major science instruments and 4 major science themes. And the research I'll be reporting on in this talk is on the science theme of the birth of stars and protoplanetary systems, which will focus on the results from just 2 of the instruments, the near-infrared camera NIRCam and the mid-infrared instrument, or MIRI. And to give you a sense for the size of the James Webb Space Telescope, it's the largest diameter telescope we've ever launched into space, with a diameter of about 21 feet and 4 inches, or 6.5 meters. Its primary mirror, that I'm actually wearing my necklaces of the primary mirror of the JWST, is a 6-sided or hexagonal shape made up of 18 segments. To give you a sense of the size, here's a full-scale model on the lawn at Goddard Space Flight Center with approximately 200 people. The JWST was built on behalf of 8 billion humans, more than 20,000 engineers, approximately 10,000 current and future observers, and about 100 scientists worldwide, with 3 international space agencies cooperating. The JWST has been a long time coming. In the inset, you see yours truly presenting a poster entitled "A Mid-Infrared Camera for the NGST." NGST stood for the Next Generation Space Telescope, and this was at the NGST Science and Technology Exposition in Hyannis, Massachusetts, held in September of 1999, over a quarter century ago. Infrared observations mean that, whoa. Yep, that's still the JWST at Goddard. So it's an infrared telescope, not visible like Hubble. So infrared observations mean that the telescope and its instruments operate at frigid temperatures, minus 393 Fahrenheit for the near-infrared instruments, and at minus 447 Fahrenheit, 7 kelvins above absolute zero, for the mid-infrared instrument. The need for such low temperatures is to avoid excess noise radiated by the telescope, its components, the sun, the earth, and the moon. This is why JWST has its immense sun shield, which is those big panels that are stretched out underneath it. That's the sun shield that radiates away heat from the sun, the moon, and the earth. And that back portion is always pointed towards the sun, moon, and earth. And the telescope is always pointed away from those celestial bodies. Another crucial reason for a space-based observatory for mid-infrared is that this is the wavelength at which Earth radiates most, around 10 microns. So observing from the ground at mid-infrared is like trying to observe dim stars during daylight. The required cold temperatures are attained by JWST's position 1 million miles from Earth, far from both the Earth and the moon, and the mid-infrared instrument needs additional cooling provided by its onboard closed-cycle cryocooler. So the results I will show from the JWST relating to a bona fide protostar later in this talk were acquired using the near-infrared camera, or NIRCam, in its imaging mode. It can operate from about 1 to 5 microns and provides an assortment of 29 filters from which to choose. It has superb angular resolution in the infrared, about 1/10 of an arc second, similar to Hubble. The JWST results I'll show for later stage young stellar system used the mid-infrared instrument MIRI in its MRS, or medium resolution spectrograph mode. MIRI operates from 5 to 28.5 microns, and it provides slightly worse angular resolution than the near-infrared instrument, but at stupendous sensitivities unattainable from ground-based observations. In its MRS mode, each image pixel contains a full spectrum from 5 to 28 microns. As for ALMA, as we previously noted, a sub-millimeter telescope requires a high dry site to be above most of Earth's absorbing atmosphere and avoiding water vapor absorption. This is why ALMA is built on the Chinantor Plateau at an elevation of 16,500 feet in the Atacama Desert in Chile, which has an average annual rainfall of just 2.8 inches. ALMA uses 66 high-precision dish antennas of 2 sizes, 54 that are 12 meters or about 39 feet across, and 12 that are 7 meters or about 23 feet across. Assuming everything else being equal, the sensitivity of a telescope depends on its collecting area. A stupendous 71,000 square feet, or about 1.6 acres for ALMA's collecting area. Now, a bit of how an interferometer works. Basically, an interferometer is a spatial filter. ALMA is trying to mimic a single 10-mile diameter antenna, which is, of course, impossible to build. The Earth's rotation is used to effectively fill in some of the missing area from the hypothetical giant antenna. ALMA can actually attain the angular resolution of a single 10-mile diameter antenna, since its angular resolution is determined by the ratio of the observed wavelength to the maximum antenna separation. Since the maximum antenna separation is 16 kilometers or 10 miles, ALMA can attain resolutions more than 4 times better than the Hubble at its shortest ultraviolet wavelength. Because ALMA is not a single giant antenna, it does have a blind spot. This is called its largest recoverable scale. This is a direct consequence of the fact that there's a minimum antenna-to-antenna separation, so angular scales corresponding to what could be sampled by closer antenna separations cannot be observed. This is caused by the simple physical fact that if you space the antennas any closer, they'd crash into each other. This limits the sensitivity of any ALMA observation to a maximum spatial extent. So if a source has structure on a scale larger than this, it will not be detected by ALMA despite its presence. For the ALMA observations of the protostars and young stellar objects I'll talk about, this spatial scale corresponds to 4.5 arc seconds for 1.3 millimeter observations and about 6.6 arc seconds at 1.9 millimeters. The third important angular scale for an interferometer is its primary beam or field of view. As we saw previously, at 1.3 millimeters, this is 22 arc seconds for ALMA. Similarly to the medium resolution spectrograph on JWST, ALMA acquires spectra at each image location. Although ALMA enables observations spanning the 0.3 to 3.6 millimeter spectral range, the observations I'll be reporting on in this talk were acquired at wavelengths of 1.3 and 1.9 millimeters, which are sensitive to emission from the cold dust in protostellar protoplanetary disks and from the cold molecular gas within them. We will now explore the powerful combination of JWST near and mid-infrared observations with ALMA's millimeter and submillimeter ones for two young systems in the Rho Ophiuchi molecular cloud core, a protostar and a later stage T-Tauri system. So this is the Rho Oph star-forming cloud, which shows the dramatic difference between optical and mid-infrared observations to drive home the point of why observing in the mid-infrared is so crucial to study star formation. The Rho Oph star-forming region is among the closest to Earth's at just about 400 light years distance, and it's a favorite of amateur astrophotographers. At left, you see a colorful picture of the Rho Oph cloud core at optical wavelengths. That's in the range of 0.5 to 0.7 microns. By eye, Rho Oph is the blackest region seen against the Milky Way's stars due to obscuration by interstellar dust. At right, you see the same region of sky imaged at mid-infrared wavelengths ranging from 3.6 to 8 microns by the Spitzer infrared space satellite. The mid-infrared image reveals many fuzzy reddish and pinkish objects. These are young stars forming in the cloud core. We can see these in mid-infrared light for two reasons. Light at mid-infrared penetrates the intervening dust further than optical light can, and these objects radiate most of their energy at these wavelengths. We will next show combined JWST and ALMA results for the protostar VLA 1623, which is circled in black on the mid-infrared image. So the expanded region surrounding the embedded protostar, known as VLA 1623, is at the location of the small black circle in the Spitzer mid-infrared image, and it was observed with JWST's near-infrared camera NIRCam at right. The JWST NIRCam image is a composite of 5 different images acquired through 5 individual filters. These 5 filters included 3 wideband filters centered at 2, 3.35, and 4.4 microns, bracketed by 2 narrow-band filters, one centered on a hydrogen emission line at 1.87 microns, and the other centered on a molecular hydrogen emission line at 4.7 microns. Notice that the protostar, whose position is indicated by the white circle in the NIRCam image, is so embedded that it is invisible at these wavelengths, despite the extraordinary sensitivity of the JWST. This is precisely why submillimeter observations were required to detect this protostar back in 1991 with the James Clerk Maxwell submillimeter telescope atop Mauna Kea in Hawaii. What you do see, however, is the extraordinary detail in the shock structures of the bipolar jets driven by the protostar. The bright star at left, illuminating the yellowish nebula, is a young early type star giving off ultraviolet radiation, which causes the microscopic soot in the cloud to re-radiate at characteristic infrared wavelengths. Also notable are the extraordinary numbers of bipolar jets powered by other young embedded stars, shredding the cloud out of which they're forming. So this slide shows the importance of spectroscopy. Spectroscopy is a fancy way of saying dispersing light or breaking up light into its constituent wavelengths. An example is the dispersing of sunlight by water droplets to produce a rainbow. Instruments that can similarly disperse light to a greater extent use prisms or diffraction gratings. At sufficiently high dispersion, we can start to discern the fingerprints of gases produced when they either absorb or emit specific wavelengths of light. Each atomic gas has a characteristic set of discrete wavelengths at which it radiates. Similarly, each gaseous molecule emits and absorbs at wavelengths specific to it. This slide just illustrates the characteristic wavelengths at which molecular hydrogen emits at mid-infrared wavelengths at 5.5, 6.1, 6.9, 8.0, 9.7, and 12.3 microns in this example of molecular hydrogen emission from a bipolar outflow powered by a low-mass protostar. The various plotted spectra, plots of brightness versus wavelength, are extracted from various positions at the locations of the colored squares on the grayscale image of the integrated molecular hydrogen emission tracing the outflow in the top image. Spectroscopy also allows us to distinguish motion along the line of sight. A spectral line will be blue shifted relative to its rest wavelength if its emitting gas is moving toward us, as is the case for the molecular hydrogen towards the northwest of this protostar, sampled through apertures delineated by the blue squares. That same spectral line will be shifted towards longer wavelengths, or red shifted, if its emitting gas is receding from us, as is the case for the molecular hydrogen gas located to the southeast of the protostar, sampled through apertures delineated by the red squares. The point of this slide is to demonstrate how bipolar outflows from protostars are detected via emission from specific molecules or atoms in their constituent gases. So in this way, ALMA discovered not one, but two distinct molecular outflows emanating from the protostellar position demarcated by A and B in the slide. The outflows were mapped by ALMA via their 13CO2-to-1 transition, that's a rotational transition of that molecule, at 1.3 millimeters. Although the JWST NIRCam image at left shows the beautiful detailed structure of the bipolar 4.7 micron shocked molecular hydrogen gas in red, it does not yield any information about gas velocities. As previously pointed out, ALMA acquires spectra at each image location for molecules with emission lines lying at frequencies or wavelengths inside the observer's specified observing bandwidth. The ALMA observations of the VLA 1623 protostellar region have exquisite velocity resolution in the 13CO2-to-1 emission line as displayed in the outflow images at right. From ALMA's line images, not one but two distinct outflows are detected. The line maps of these two outflows have been vertically offset for clarity. In both ALMA images, blue represents blue shifted gas moving towards us, and red represents red shifted gas moving away from us. The dashed white lines are the inferred position angles of these oppositely directed molecular jets. Note the opposite senses of their velocity distributions. Outflow 1 has its blue shifted lobe, gas moving towards us to the southeast of the protostellar position, whereas outflow 2 has its red shifted lobe, representing gas moving away from us to the southeast. So here we continue to see the power of ALMA combined with JWST. Again, we see the NIRCam image, which serves as the background image at the top right. The outflows are observable in the NIRCam image only in the narrowband filter at 4.7 microns. which transmits the 4.7 micron emission of molecular hydrogen and is represented by the red color in the color composite image. Were we to exclude this narrowband filter image at 4.7 microns from the combined color image, the outflows would disappear. In fact, the presence of a protostar here was first inferred from the detection of its large-scale bipolar outflow discovered via its 2.6 millimeter CO emission with no apparent source at the center. You see, the JWST cannot detect the protostar directly. It's still too dust enshrouded. However, the insets show the ALMA detections of the cold dust disks of not just one, but of several protostars as delineated by the white contours in insets B and C. In fact, this protostellar system is now revealed to be comprised of 4 different objects. Inset B shows 3 objects at the protostar's position. The proto-binary making up source A, labeled capital A little a and capital A little b. In inset B, separated by just 30 astronomical units or 30 Earth-Sun distances, and which is surrounded by a circumbinary disk, along with the nearby protostellar companion labeled capital B. The orange cone-shaped structure detected by JWST at 4.4 microns emanating to the south of source capital A little a is scattered light from the cavity created by the blue shifted outflow. A nearby protostellar companion is labeled capital B. A more distant young source labeled W is displayed in inset C. Referring to source W in inset C, we are seeing an edge-on disk. We know this both because of the elongated shape of its cold dust emission, as outlined by the white contours representing the 1.4 millimeter emission detected by ALMA, and from the characteristic appearance of scattered light seen in the JWST image in orange. That's what a flared disk looks like in scattered light, edge on. The images at the bottom show velocity-weighted emission from cold gas imaged by ALMA of these sources from C17O gas, such that gas moving towards us is shaded blue and gas moving away is shaded red. And by fitting the observed velocity structures in these disks, the central source masses can be derived from Kepler's laws. So in this manner, the combined mass of the proto-binary is found to be just about 1/3 of a solar mass. Source B is the most massive at about 1.9 solar masses, and source W, the edge-on disk, harbors a central object with 0.6 solar masses. As you see, real star formation is a messy process. The artist's conception of the physical structure of a protostar at left assumes a single star forming by itself. However, we know that most stars are found in binary and even higher order systems. In this prototypical protostar in the row of cloud core, we're finding that star formation proceeds from turbulent fragmentation of the cloud core's gas. Next, we'll discuss some spectacular results for the more evolved, roughly 2.5 million year old young stellar object named WL20 from combining JWST mid-infrared instrument, medium resolution spectrograph data, and data from ALMA. So our source that we're going to be talking about now is circled in white, and it's called WL20. So here's an expanded view of the small red source circled in white here. So that's it, an expanded view of what happens if you look closely at that source. That object was already known to be a young triple system from previous ground-based observations shown in the top panel. Unlike the sun, many stars are found in binary or higher order multiple systems. You might wonder, so what? So we have a young triple system. What's so special about it that it merits further study? The answer has to do with the peculiarity of the third southernmost component of the system. It's the faintest of the three at the shortest infrared wavelengths, as can be seen in the 1.6 micron image at the top left. However, as we proceed to longer wavelengths, this southern source gets brighter relative to its northern neighbors, until at the longest mid-infrared wavelengths, at 7.9 to 12.5 microns, it's the brightest of the three. In addition, the southern source is much more dust obscured than its northern neighbors. We estimated the age of the northern sources to be about 2 to 2.5 million years. However, the peculiar brightness behavior of the southern source is consistent with the appearance of protostars that are less than 1 million years old. How could this be? So we took a look with the James Webb Space Telescope's mid-infrared instrument and found that the southern source, first of all, is actually comprised of two. In the next slide, we focus on the region outlined by the white dashed lines at the bottom of this slide in the new JWST image we obtained of just that source. Remember, it's a very small field of view. Here's the appearance of the outlined region from the last slide at 4 specific wavelengths at which ionized iron, ionized nickel, argon, and neon radiate. The white circles in the neon image at lower right indicate the locations of the 4 sources of the system. Remember, the medium resolution spectrograph provides us with the entire spectrum from 5 to 28 microns at each pixel. White arrows point to each of the jets to guide your eye. We were absolutely stunned when we first saw these images of the ionized twin jets in 9 different mid-infrared spectral lines emanating from each of the 2 sources, which were previously thought to be one. The jets must be extremely hot since they are composed of ions, which are individual atoms with an electron stripped away. Only the mid-infrared instrument known as MIRI in its medium resolution spectroscopy mode was capable of making these discoveries. It delivers images at hundreds of mid-infrared wavelengths of the same object, enabling the identification of gases of different compositions, since each element radiates at its own unique wavelengths. And this has to do with the detection of the associated cold dust disks, for which we needed millimeter or ALMA observations. So as mentioned previously, millimeter observations are sensitive to the presence of cold dust in protostellar disks and can penetrate the intervening dust more readily than infrared light. At left, you see a millimeter wave observations of the system acquired with the now defunct Owens Valley Radio Observatory's millimeter interferometer, which was comprised of 6 10.4 meter diameter antennas at the time. The positions of the infrared sources detected from the ground are indicated by the white crosses. Note that neither of the northern sources, whose positions are labeled East and E and W, were detected, and that the southern source was unresolved. At right is the ALMA image of the same target. Remember, ALMA has 66 telescopes. Each of the northern sources is detected, and the southern source is well resolved. To get a sense of the power of ALMA, it took 18 hours of integration time to produce the image at left, and just 30 seconds of on-source integration time to produce the image at right. So ALMA discovers twin edge-on disks in the system. So as noted in the previous slide, ALMA detected the 2 northern objects, WL20 East and West, each with disks of their own that would extend out to just beyond Saturn's orbit, where they located in our solar system, although they could be even smaller given they remain unresolved. Disk dust masses of just 3.3 Earth masses are derived for the eastern component, and just 3.6 Earth masses of dust for WL20W. The lack of any detected CO emission with these sources leads to the firm conclusion that the gas to dust ratio in these disks is at least a factor of 10 lower than the interstellar value of 100, meaning that at this stage of their evolution, at just 2 to 3 million years, much of the disk gas has already disappeared from the protoplanetary disks. Mechanisms for the disappearance of the disk gas would be accretion onto the central star, with replenishment from any circumstellar material having ceased, being shed by disk winds, or accretion into newly formed planets. The ALMA structure associated with the southern source could easily have been misinterpreted as a single large disk with a central gap in it if we did not have the JWST discoveries of a new twin or of the twin parallel ionized jets in the system. With that knowledge, we can correctly interpret the ALMA image of the southern object as a pair of aligned disks seen edge on. Each of these disks would extend out to Pluto's orbit from the sun, having diameters about 100 astronomical units each. The derived disk dust masses are 24 Earth masses for the WL20SE disk and 42 Earth masses for WL20SW. Modeling the measured ALMA gas fluxes, which are not shown here, the combined gas mass for the twin disks is just 100 Earth masses, but the total gas mass remaining in these disks could be as little as 2/3 of an Earth mass if we allow for selective photodissociation in the models. This means that substantial planet formation has already taken place after just a few million years. So here we show the synergy between JWST and ALMA observations of this young multiple system so far. At left is the ALMA image of the cold, dusty disks associated with each component of the quadruple system. At right, we have the combined jet emission detected by the JWST from 3 different spectral lines, iron, nickel, and argon, superposed on the ALMA disk image. This combined image beautifully highlights how the jets discovered by JWST have their origins in the edge-on ALMA disks. But that's not the end of the story. To our amazement, JWST also revealed an hourglass-shaped biconical structure in molecular hydrogen heated to 2400 Fahrenheit, which you see in the left panel. In addition, the entire JWST field is suffused with hot ionized neon gas, which isn't shown here. For reference, the white circles indicate the positions of the 4 sources in the left. The apex or narrowest part of this molecular hydrogen cone is centered on the twin sources with the cone symmetry axis parallel to the twin jets. Referring to the ALMA image at right, molecular hydrogen gas does not emit at the wavelengths to which ALMA is sensitive, but the next most abundant interstellar molecule, CO or carbon monoxide, does. ALMA is sensitive to much colder gas, say at temperatures of -457 Fahrenheit, which is about the ambient temperature of the cold interstellar gas out of which young stars form. Mapping the distribution of the cold cloud gas surrounding this young system, we find almost a perfect anti-correlation between the hot molecular hydrogen and the cold carbon monoxide. From these data, it is clear that not only is there no cold gas outflow associated with any of the WL20 sources, but the past outflow activity has completely obliterated the original cloud core from which the system formed, with less than just a few hundredths of a solar mass of cold gas left in the system. Here, we put all of the JWST and ALMA pieces together. At left is shown the hot biconical molecular hydrogen gas in blue, with the field of view of the JWST observation outlined by the blue rectangle. In red, we see the larger scale map of the surrounding cold gas detected by ALMA. Notable, as I mentioned previously, is the spatial anti-correlation of the hot and cold molecular gas. The lack of any infall envelope surrounding this system means that the only source for the hot molecular hydrogen is from the disks of the system, which lie at the cone's apex. The hot molecular gas must originate in wide-angle disk winds. At right is an artist's conception of the system. It shows the twin parallel ionized jets detected by JWST in iron, nickel, argon, and neon, and the twin dusty disks detected by ALMA. The hot biconical molecular hydrogen wind is depicted in magenta. The nearly complete destruction of the primordial gas clouds out of which the system originally formed, mapped from the cold gas emission by ALMA, is represented as the billowing orangish clouds to either side. In summary, we've seen the extraordinary synergy for gaining detailed new insights into the complex processes of star and planetary system formation by combining observations from the James Webb Space Telescope and the Atacama Large Millimeter Submillimeter Array, the former tracing the hot and warm components of gas and dust, the latter sensitive to much colder material and penetrating deeper into the star-forming cloud cores. Thank you. That's it.
All right, well, let's give our speaker a virtual round of applause.
Thank
if you can figure out how to do the reactions or whatever. They change it on Zoom all the time, so it's like, I don't know even how to do it anymore myself. Used to be able to have little clapping hands. Oh, you all figured it out. Okay, you're ahead of me. But yes, I hope you all enjoyed hearing about like a really cool discovery that, took two of the best telescopes in the world to make, because I was pretty darn impressed when I heard it the first time. So I hope you all liked it. Don't forget, if you have any topics that you want to hear speakers talk about, send me some mail with your ideas and I'll look for speakers for our fall meetings.
Okay.
Awesome. Before we sign off, I just want to remind everyone we have a little survey to capture your thoughts on the talk. We do this every month if this is your first meeting, and it's the same questions every month. I will go one question at a time, and you'll enter your answers in the chat. Let me just copy this. So my first question is, what takeaways are you leaving the meeting with?
And I should say that we ran out of time to have more questions for our wonderful speaker, but I was trying to do a good job answering questions. So she might want to read the chat and see all the questions.
Oh boy, I have to stop screen sharing in order to see the chat because my cursor is black and so's the background of my slide. Is that okay?
Well, yeah, you're not screen sharing anymore.
I'm screen sharing now.
Brianna took it away.
Oh, okay, good. Then I don't have to worry about it at all. Great.
But if you want to read what everybody was asking, hopefully I answered the questions correctly.
I'd be very happy to answer questions once you're done with the survey if people want to hang out.
Yeah.
Well, we'll see what happens.
Mm-hmm. And if you don't have anything to share, you can just write nothing to say right now, or NA, or no takeaways, so that I know you've answered the question. I'll give about 30 more seconds to answer question 1 if you're still typing. All right, if you're still typing, go ahead and finish up and click enter when you're ready. I'm going to move on to question 2. What good things happened in the meeting today? Again, I'll give about 30 more seconds for this question. So if you're still typing, finish up your thought. And I'll move on to question 3. And that is, what should we do differently next time? All right, and then finish up your thoughts here. I'm going to move to the last question, which is similar to this one. What did you want to happen but didn't happen today? When you're done, you can sign off and leave the meeting. Mary has offered to stay on a little longer, so I have to go, but we could leave the Zoom room open if you guys did want to discuss. And she has the time. You can stay.
Yeah, I do.
But otherwise, we're done for this month. Again, we're taking a break in August with the monthly speaker series, but we'll be back in September. So if you're a
But
scholar,
don't forget, we have our 3 project showcases in August, so it's not like we're really taking a break in August.
right? Well, for the 2025 interns, we'll still see you every Wednesday at this time. But for scholars, we're taking a break until September. All right. I'm going to stop sharing. Thanks everyone for filling out the survey. And that's it. Mary, if you're open to out loud questions, maybe folks can use the raise hand function so that we're not all speaking over each other.
Oh, I see.
I see Sid has his hand up.
How do I, oh boy.
Can you see like a little hand there? And then you could just call on the person with their hand up.
Well, please go ahead and ask your
Yeah, go
question.
ahead, Sid.
Can't see.
So,
Ugh.
I appreciate the part in the presentation about about spectroscopy and but the was the reason why you mentioned it because you can identify stars by the elements they produce in their bipolar outflow. Does that mean
Yeah,
that every single element radiates, energy at a different frequency?
yes. There are many questions in there. Yes, every single element does have its own distinct set of frequencies or wavelengths that it emits. That's true. I mentioned spectroscopy for several reasons. One is that that's the way we can tell we're seeing iron or neon or the argon or the other gases that we saw in the jets. It's because we see their characteristic spectral lines. I just didn't have time to show you what all their spectral lines were.
What does spectral lines mean? Does that mean
It-
the wavelength at which it emits light?
Yes, that's exactly what it means. Yes, and it's
Okay.
just that each element emits at a very narrow band of frequencies or a narrow band of wavelengths, and that's just the common terminology that's used to describe that.
So
Did I
that
answer your
wavelength,
question? Mhm.
yeah, so that's narrow band of frequencies. It doesn't change depending on how much energy is in the element.
No,
It doesn't
what changes
change?
if it's more energy,
Oh.
then it's brighter.
Oh,
Then
okay.
it's brighter, but it's still at the same wavelength.
That makes
And the
sense. Thank you.
And then the other thing we can learn from the spectral lines is if we have enough dispersion, or it's called resolution, or fine enough sampling of that frequency band, we can tell the motion towards us or away from us. So towards us, it's called blue shift, and away from us, it's called red shift, because in the optical, those are the colors towards which the rest wavelengths shift. If they're moving towards us, it's towards the blue part of the wavelengths, the spectrum, and red is away from us. So we can tell motion in that direction from the spectral lines, which is how we can tell, parts of the outflows are moving towards us and parts are moving away.
Okay. Thank
In
you.
a given line, in a given line.
In a given
Yeah.
set.
Yeah, the different
Yeah.
chemical elements all have their own specific frequencies at which they have electrons jumping from one orbital to another, and that makes a photon of that frequency. And so the spectral lines are like chemical fingerprints that tell you what chemicals are involved in that gas. And their characteristics lines will shift depending on if they're going towards us or away from us. But
Okay.
there's only one major object in the universe that's actually going towards us, and that's the Andromeda Galaxy, which is part of our local group.
Really?
All the other
And
galaxies that are not in the local group are moving away from us.
And in fact, it's spectacular, but we're already crashing into Andromeda there's this huge halo of ionized carbon. I couldn't believe it. That's a fairly recent discovery that surrounds both, it's the intergalactic medium that surrounds both Andromeda and Milky Way, and they're already touching.
Although
Sorry,
it's
that's
it's not what you normally think of when you think of a collision, because the particles are so spread out that they don't really hit each other. Everything just sort of passes through each other and exerts gravitational energy on each other, but without like any explosions or anything blowing up like you normally think of when you think of a collision.
So they're
Any
just
more
kind of
questions?
merging.
They're kind of merging, but yeah, but they are definitely approaching each other. We won't live long enough to see anything dramatic happen, that's for sure.
All right. Thank you very much.
Any other questions? Oh, well, whoever has a question